right, we're going to look at an example of pumping water out of a tank. So we've got a water tank that's shaped like an inverted cone with a height of 6 meters and a base radius of 100 or 1.5 meters. If the tank is full, how much work is required to pump the water to the level to the top of the tank and out of the tank? So the first thing that we're going to do with this, and this is what we do with a lot of these like pumping problems and problems that are, sorry about that, my cat jumped on my iPad, and the hydrostatic force problems, is we're going to set this up on an axis. And there's lots of ways to do this, but I tend to set this up so we've got the x-axis there, horizontal as we're used to, y is vertical, and then I often set this up so that the origin is one of the points that we're going to use for our shape. So we're going to put that bottom part or the tip of the cone down there at 0, 0. So that means up here at sort of the top edge of the cone, we're at the point 1.5 and 6 because that radius goes out to 1.5 and then the height is 6. So then what we also want to think about is that we're going to slice up this shape. And we want to think about, okay, if we've got a slice of water here, what's it going to take for us to get this little slice of water up and out of our tank? So our slice of water, how tall it is or the thickness is delta y, because we're slicing up the y-axis. And then the volume of a slice, because we need to know that, how much water we're moving out. The volume of a slice is going to be pi times the radius squared times our height. That height is the thickness of our little cylinder that we're moving out. So when we make a slice, that is making a little cylinder. So we're going to have pi times the radius squared times delta y. That's how thick that slice is. And then our radius, well, our radius is going to depend on where our slice is, because it's going to go from that y-axis out to the side of our cone. So what we need is the equation of this line, because that's going to tell us what our radius is. So that line, it goes through the points 0, 0 and 1.56. So we can find its slope pretty easily because one of the points is 0, 0 that we're using. So you get 6 divided by 1.5, which is 4 for our slope. And then in putting this in point slope, we can use that point 0, 0. So we get y is equal to 4x. Now, this is our line, but what we need to do is change this to 1/4 y is equal to x, because our variable is going to be y, because we're slicing up the y-axis. So we need to solve our equation in terms of y. So our volume of our slice is going to be pi times that radius that we got, which is going to be 1/4 y squared. And that's going to give our radius at whatever point we make our slice. So then the work required for this is going to be to move this like singular slice. It's going to be the volume of a slice times gravity times the density of water, and then times the distance that the water has to move. So our volume of our slice is that pi 1/4 y squared and then delta y. Gravity is 9.8 when we're in metric. This is a number we will always give you. You don't have to have that memorized. Density of water is 1,000. Again, that's a number we'll give to you. And then how far that water has to move. So we've sliced it there at a point y, and it's got to get up and out of our cone there. And so it's got to go up here to 6. So the distance that it has to travel is 6 minus y. So to kind of help that make sense, I often think about that. Okay, what does that 6 minus y mean? So let's say y is here at 2. It's got to move 4 meters to get up and out of our cone. If our y was here at 5, 6 minus 5, it would only have to move 1 meter to get up and out of the cone. So now this essentially is our integral. We just need to turn it into an integral. So the work is going to be, well, the cone is all the way full of water, so it's going to go from 0 all the way up to 6. If it was, only full of water to 5, we would only go from 0 to 5. So those limits of integration, that has to do with how much water you actually have to have in your tank. And then we'll have our pi, and then we can write that as 1/16 y squared. This delta y, that's going to turn into your dy. And then we have our 9.8, and then our 1000, and then our 6 minus y. So there's our integral. It's not terribly difficult to take this integral, that pi over 16 and the 9.8 and the 1000. You can pull all of those out in front, and then you've got y squared, 6 minus y dy. And that's the nice thing about these work problems, is that most of the time, how we have these set up, once you get to the setup of your integral, you usually end up with, a polynomial, or even sometimes just a linear function that you have to take the integral of. And I will let you do that part, and you'll get 66,150 pi joules of work.